L systems. So one way to procedurally generate trees is to start with a trunk. So we're starting with just one segment here. Then let's split this segment into 3 other segments at some specific angle. And we continue doing that. These new segments we split again into 3 new ones. When we do that, the resulting tree is kind of symmetric and kind of unnatural. So to make it more natural, we could shorten the branches. So each branch is going to be 75% of the length of the previous branch. This looks more natural because in the real world, the new branches that grow are also smaller than the parent branch because they have had less time to grow. Next, we can add some randomness to the angles. So they don't all have to be 50 degrees. So maybe there's some kind of a random range, and some of these angles will be 43 or 63 degrees and so on. And we can add even more branches. And then we can keep generating these trees until we find the one that we're happy with. Of course, we could also play around with the parameters. So how much shorter should the child branches be? What's the default angle that the child branches grow at? And what's the randomness factor? So how random will these new angles be? Now a bit more rigorous way to generate those trees is Lindenmayer systems, or L systems for short. So they're kind of a way to generate and store self-similar objects. These were developed by Aristide Lindenmayer, and the book Algorithmic Beauty of Plants was published after Lindenmayer had passed away by his friend. And this book details the Lindenmayer systems and how they can be used to generate these different self-similar objects, including trees and plants and so on. Now before we talk about Lindenmayer systems, we have to do a small recap on formal grammars. So some of you have probably learned formal grammars in your previous courses. But to recap, formal grammars consist of a set of non-terminal symbols, n. So those are symbols that can be changed into other symbols by the rules. Or in other words, they don't terminate the derivation. Then there's a set of terminal symbols. Now these are symbols that cannot be changed, so those two terminate the derivation. Of course, we have a set of rules that define how we can change these non-terminal symbols into either other non-terminal symbols or terminal symbols. And we also have a starting axiom S that we start our derivation from. So this will be the starting point of our derivation. Now formal grammars are easy to understand with an example. So let's say we have a set of non-terminal symbols that consist of a capital A, set of terminal symbols that consist of a lowercase a, and 2 production rules. One transforms the capital A into lowercase a, and another transforms the capital A into 2 capital A's. We start with a starting axiom capital A, and now we can choose what production rule we apply. So let's apply the second rule that transforms this capital A into 2 capital A's. At the next step, we again have a choice to make. So this time let's apply the first rule that transforms a capital A into lowercase a. And we apply it on the second capital A here, transforming it into a lowercase a. Now we can't transform this lowercase a anymore, but we still have one capital A left. So let's use the second rule again that transforms this into 2 capital A's. Next, we'll use the first rule to transform the second capital A into a lowercase a, and we can use the first rule again on the last capital A that transforms it into another lowercase a. So in this particular example, we started with a capital A and ended up with 3 lowercase a's. Of course, if we would have made different choices when we picked the rules, we would have ended up with a different word at the end. So, Lindenmayer systems. They're a formal grammar, so with Lindenmayer systems we also define these sets, but they're also a parallel rewriting system. All the non-terminals in the word are changed together in each iteration. So previously we just picked one non-terminal symbol and then picked a rule to apply. But with parallel rewriting systems, in one iteration, all of the non-terminals that can be changed will be changed. We will look at the Lindenmayer system that is bracketed, because bracketed systems can define branching, and with trees we want branching. We will look at the stochastic system. So stochastic systems have rules that have probabilities. So there's a probability for each rule, how likely it is that that will be picked. The Lindenmayer systems we'll look at are also context-free, so we replace the full left-hand sides of each rule. And we'll also look at parametric systems, how symbols can have different parameters assigned to them. So here's an example of an L system that generates trees and is bracketed. We need to define what symbols are we using and what do they mean. So here we're using a symbol F to represent a tree segment, and F is a terminal symbol. whenever we have the letter F, we will not be able to change it into something else. We also have the letter B, let's call it baud. So those bauds are non-terminals, and these can be changed. Then we have the letters plus and minus. Those indicate the rotation, and for now let's use our 50-degree angle again. Plus will rotate in one direction, and minus will rotate in another direction. And we'll use these square brackets to indicate branches. You can think of these branches as kind of saving and loading the state we are at. So when we're drawing the tree, when a branch starts, we continue drawing, but when that branch ends, we revert back to the state where we started that branch. And let's have one rule. So a rule is that bauds, these letter B's, get transformed into these three branches. And you can see that the first branch here in these square brackets first rotates, then draws a tree segment, and then creates another baud. The second one doesn't rotate, it keeps continuing forward and has another baud, and the last one rotates to the other direction. Our starting axiom is FB, which means that we have one tree segment here and it ends with a baud. Now if we iterate on this FB, then we have only one rule and we apply that one rule, getting this state. So this is after the first iteration. We have a tree segment, and from that tree segment, from the previous baud that we had up here, so this one, we created three new tree segments that end with bauds and are either rotated to one side or another side or continue straight. Now we can apply another iteration, and again we're changing these bauds into three new tree segments, each ending with a baud. So this is how bracketed L systems work. Each iteration, we are rewriting all of the non-terminal symbols, all of the bauds, according to our rules. But we can see that this tree is also very symmetrical, just like the one we had before. So one way to add some randomness into the result is to use a stochastic L system. Now stochastic L system with these specific rules here would be able to generate different trees. Let's look at these rules. So again we have this non-terminal symbol B that gets transformed into something, but each rule now has a probability. And we have several rules with the same left-hand side. These probabilities of the rules with the same left-hand side need to always sum up to 1. So there is always 100% chance that we pick one of those rules to replace the baud here, for example. But each of them has their own probability. So there's 1 in 3 chance we pick the first one, the one that creates us 3 branches. There's a 1 in 3 chance that we pick the second one, that creates a branch rotated to one side and the branch forward. And there's a 1 in 3 chance that we pick the last rule, that creates us the branch forward and the branch rotated to the other side. And now you can see that depending on which specific rules we have picked in these 2 iterations, we can get all sorts of different structures here. Now a parametric L system would be the one where we can also write in different parameters for these operations. For example, this plus, this denoted a rotation by 50 degrees, but we could add some brackets here and say that this particular plus is rotation by 39 degrees. And we can also have a parameter for the length of each segment. So for example, this segment, this F here, would be 0.56 units long. However, if each new child branch is always 75% of the length of its parent, then we could also include this length calculation into the rendering algorithm. Because these numbers, we can calculate these. This 0.56, that is 75% of 0.75. So we wouldn't need to waste space in the actual string here. But it of course depends on your application. Maybe this is not that cut and dry that it's always 75%, but rather maybe an artist changes the lengths of these branches here, so then you would need to encode the lengths into the string. So, Lindenmayer systems are a rigorous way to procedurally generate and store self-similar structures. Now this self-similarity, you can also call it like a recursive structure, or maybe a fractal structure, or there might be some more names that denote this self-similarity. You can see this self-similarity in our tree structure, for example. So each of these bauds spawn new tree branches, or maybe some random number of branches, but still the same algorithm is applied at each level, creating this self-similar object. There are 3 branches for this node, but there are also 3 branches for the parent node, and so on. I do recommend you to check out this Algorithmic Beauty of Plants. It's a free book online which you can open, and it describes all sorts of different beautiful patterns that are found in nature and rigorous mathematical systems to create them in a computer. If you Google L systems, you can also find different online demos. For example, on this site, you can create different patterns and organic self-similar structures like the one on the right here. My own bachelor thesis was also actually about generating these trees with L systems. And here's a tree I generated for my bachelor thesis. And these were the rules that I used for this particular tree. Now this is a 3D tree. And in 3D, the process works exactly the same, except that I had some new symbols here that represented rotation around the x-axis. So when we had this plus and minus, then these kind of rotated around the z-axis, so left and right from our viewpoint. But in 3D, we can also rotate backwards and forwards. I also use these different kinds of paths to create more variation into the trees. So F transformed to H and G transformed to some other H and G, H could transform to H or H and F, and so on. So L systems is all about coming up with these rules. How should your self-similar structure behave? How should it grow? And these rules kind of represent that. In SysUlearn, there is also this neat example here. So we have this three-dimensional tree. We can increase the number of iterations we're doing, and we can also increase the probability of different rules. So if we only use this one rule, then we're getting this very sad looking tree here. But if we change these probabilities, we can create more chaotic trees. And decreasing the number of iterations gives us smaller trees. So from this video, you should now understand a very simple tree generation algorithm, the one we saw in the beginning, where we just iteratively added new branches, and you learned about different parameters such an algorithm might have, for example the randomness in the angle. We recapped some formal grammars, remembered the sets of non-terminal and terminal symbols, the set of production rules, and the starting axiom, and we learned about Lindenmayer systems that are parallel rewriting systems, rewriting every non-terminal symbol in one iteration. We saw versions of Lindenmayer systems that are stochastic, so there can be different rules with the same left-hand side, each having a probability that that particular one will be picked. We saw a bracketed system for these three branches. We also saw parameters and how we can encode them in the string, for example different rotation angles and lengths of our tree segments. And we used context-free L systems. So we always replaced the full left-hand side when using the production rule. And we saw how we can interpret these strings that L systems give us for procedural tree generation.